well, proportional to 1 over this uncertainty in the frequency, right? 1 over delta tau, right? So here's the delta tau underneath. So you now have this. So the uncertainty in the position is now this term here. Now, so now let's concentrate on the uncertainty in the frequency. So we can use this formula. Now let's say this is a fairly small value compared to 1. Well, yeah. So let's say this is fairly small compared to 1. So that means effectively this frequency is pretty much the same as the frequency when it's not moving. So the frequency of what? Let's see what the photon. Yeah. So let's assume roughly that this frequency equals this frequency. All right. So so if we want to find the uncertainty in this frequency, so put a delta here and delta on both sides, and you'll get this frequency sub-zero, delta v, and v now is the velocity of your particle, remember, little v, divided by c. So delta will be delta here, or you can take the delta inside because this is a constant. You get delta v over c, which is here. But we've just said that this value here is pretty much the same as this one. So approximate this one by this one. Right? Which that's what's being said here. Okay. So therefore we can rewrite this. We just change this here to just this term. Right? So that gives us now a measure of the uncertainty in the frequency of the photon shot out. Right? It's this term here. Now let's go back to our uncertainty in position. We have this formula. Right? So now we have this uncertainty in the frequency of the particle. We have a formula for that. That's this. So take this and plug it into here. Now if you do that, you can rewrite your delta x, the uncertainty in position, as so it's just h, this frequency of the measured frequency of the photon. All right. So your delta frequency you can replace by this. Now let's see, these frequencies, those two terms cancel. The speed of light, two terms here, they cancel. And what are you left with? You can bring this delta v over to the left-hand side. The m as well. So you'll get m delta v. The delta v here, that's the uncertainty in the velocity of the particle. Okay? So if you multiply that by m, that's the uncertainty in the momentum of the particle. Right? So you bring delta v and m over to the left-hand side, and you get delta x, delta p, and what are you left with then? The c's have gone, these frequencies have gone, the delta v and m's been brought over, so all you're left with is h. Okay? And therefore, delta x, delta p is roughly equal to h. Now, a lot of physics and a lot of reasoning there. Definitely harder than this more hand-wavy approach, but at least now we have derived h. We've actually brought h, Planck's constant, into it. All right. So there's a somewhat more rigorous, more physics-based reasoning behind it. And later in the course, we will derive even more accurate estimation of what this constant here is. Now, strictly speaking, this product of uncertainties is actually greater than some minimum constant. So when we derive the Heisenberg uncertainty principle with greater accuracy, this product of uncertainties, delta x, delta p. So uncertainty in position measurement times uncertainty in momentum measurement. It will be greater or equal to some constant. Okay, and the constant's of the order of Planck's constant. So these uncertainties are very, very small. Like in today's, well, in the human scale world, these uncertainties are really tiny. So we don't notice the Heisenberg uncertainty principle in daily life because this phenomenon, these uncertainties are just so tiny, tiny. All right. So new topic. Well, I'll start off with a bit of a story. So Schrödinger, Erwin Schrödinger, Austrian mathematical physicist. He was a bit of an expert in differential equations and wave equations and such. And he was getting very interested. This is like let's say mid-20s, more or less. And he went along to, he'd heard about this amazing suggestion coming from Paris, from de Broglie, that particles might have wave-like properties. So he was attending a seminar in Vienna, in Austria, and one of his colleagues in the seminar made the comment, well, if these particles have wave-like properties, there should be a wave equation to describe that waving motion of the particle. And Schrödinger was particularly impressed by that comment. He took it really to heart. He thought, that's a valid comment. There should be a wave equation for the wave-like properties of the particle. Now, he was an expert in such things, wave equations and differential equations and such like. So he took it upon himself to try to find a wave-like equation, a wave equation for wavicles, for de Broglie's wave-like particles that have wave properties. Now, the story goes, he was a bit of a ladies' man as well. He had a string of girlfriends at the same time, all through his life. So one particular vacation, he went to a ski resort with one of his girlfriends, and I guess got inspired, or maybe just thinking about it. So during that time, he, in a quiet moment, he sat down and really started to think about the possibility of a wave equation for particles. And now the derivation that I'll give you here is not Schrödinger's. Schrödinger used a much more complicated method involving, well, it's something I'll do in advanced classical mechanics at Masters 1, 1, 2, or let's say 1. First year Masters level, I'll be giving a whole course on classical mechanics, Lagrangians, Hamiltonians, and such things. Hamilton-Jacobi equation, canonical transformations, and whatnot. Anyway, Schrödinger knew classical mechanics very well, so he used that type of approach to derive his wave equation. Now, we won't use it because his method was much more complicated. That's often the case in scientific discovery and mathematics. There's the same thing. The genius pioneer often discovers the phenomenon, or some result, often in a quite complicated way, in a sort of roundabout way, and then somebody else comes along and takes that result and simplifies it, finds an easier way to do it. That happens again and again in both math and physics. Right? So we're going to we'll derive here Schrödinger's equation, which is very important in quantum mechanics. In fact, the next, I don't know, I need to check, at least 3, maybe more, chapters in the textbook applying Schrödinger's equation to different situations. So Schrodinger's equation is critical to quantum mechanics. So the next 1, 2, 3, 4, and in a sense, well, at 4 plus, at 4 and a bit chapters, the next chapters in the textbook use Schrodinger's equation. Applying the equation to differing situations. All right. So, well, this is not the Schrodinger derivation. This is a more textbooky, undergrady, more or less type derivation, much easier to understand. Now, so where do you begin? Well, you know certain things. You know that de Broglie has suggested that the wavelength of the wave-like phenomena associated with a particle, and I'm being deliberately vague because it's very hard to put words to these concepts. How can a particle, which is sort of like a dot, a point, have wave-like properties? Now, de Broglie himself, his vision, he imagined that a particle was actually a kind of wavicle, which you can imagine is sort of like a surfboard rider. So imagine a surfboard riding on a wave. So for him, a wavicle had particle-like properties, like that was the surfboard, or if you like, the surfboard with the surfer, the person on the board. So that was your particle, by analogy, and surrounded by waves. And the wave, in a sense, is carrying the surfboard and the rider. Right? In a sense, the wave is carrying the particle. So the term that was used for this phenomenon is called pilot, P-I-L-O-T, pilot wave theory. And so you can imagine that this particle is in a sense guided or piloted by the wave, and that was de Broglie's vision. So when de Broglie got invited to the famous Solvay, S-O-L-V-A-Y, I think. Solvay was a